Okay, good afternoon. This is one of my favorite weeks. You'll see why today. What we're talking about is trees, which are kind of two-dimensional hierarchical data structure. Unlike lists, which we talked about last week, there's nothing about trees built into scheme. It's entirely an abstract data type that you can build however you want. We're going to look at actually various alternative ways of doing it. But first, let me start with what are trees for? Why do we want a hierarchical data structure? First reason is to represent a hierarchy. So this is a small slice of the world tree. So there's actually a lot more countries than this that you don't see. But the first level is just the world, and then there are some countries, and some countries we just hang cities off of, and in the US we have these things called states, and states have cities in them. And then there's this weird thing, which is the United Kingdom of Great Britain and Northern Ireland. And Great Britain is in turn divided into England, Scotland, and Wales, plus a couple of uninhabited islands. I think the last Manx person died a while back. And those have cities. So here's Liverpool, the center of the universe. Notice, by the way, we'll talk about this in a bit, that there's a Cambridge, Massachusetts, and there's also a Cambridge, England. So that will get interesting in a bit. So one use of a hierarchical data structure is to represent a hierarchy. Duh. Here's another one. This thing is called a binary search tree. What makes it a binary tree is that each node has at most two children, and the children are explicitly divided into a left child and a right child. So 33 here has a left child but no right child, whereas 105 has a right child but no left child. So that's what makes it a binary tree. What makes it a binary search tree is every node has the property that the nodes to its left underneath it are smaller than this datum, and the nodes to the right underneath it are bigger than this datum. Okay? That's what makes it a search tree. Now, there's nothing inherently hierarchical about these numbers. It's not that, 25 plus 92 adds up to 47 or anything like that. The position of numbers in the tree is kind of arbitrary as long as it comes out pretty well balanced. You throw things in at random, it probably will come out pretty well balanced. The value of the hierarchy is if we want to do a search for something that's in this tree. Remember, searching through a list takes time theta of n, proportional to the number of elements. So let's say I'm looking for the number 70. So I look at 47. I say 47 is smaller than 70. Therefore, I don't have to look at any of these, because they're all smaller than the number I'm looking for. So now let me look at 92. That's bigger than 70. So I don't have to look at any of these. So now I look at 81. That's bigger than 70, so I don't have to look at this. I look here. That's less than 70. And so I look at its right child, but there isn't any. And therefore I know that 70 is not in this tree. And to find out, I only had to look at 4 nodes. Okay? So searching in this tree turns out to be theta of log n. We use LG as an abbreviation for log to the base 2. So that's where we're using a hierarchical data structure not to represent a hierarchy, but to represent an ordering in an efficient way. Okay, and then finally, over here, we have what's called a parse tree. And this one represents the expression that you usually see written as 3 plus 4 times 5. That's what's called an in-order traversal of the tree. We'll get back to this later. I started on the left, then the node in the middle, and then the stuff on the right, and for that, recursively, it's left, middle, right. It can also be done in prefix form, where I start with the operator and then put the operands, and then we get plus 3 times 4, 5, a notation you've seen before in this course. And there's also postfix, in which I say 3, enter. So we're going to do the operands first. So here I'm done with 3. Now I do all this thing, operands first. 4, enter, 5, times, plus. And that notation is called reverse Polish notation. It's used by HP calculators. So all of these ways of traversing the tree are useful. Any compiler or interpreter for a programming language builds a structure very like this from the expressions that you type. No matter what the surface form of the language is, it ends up with a tree like this in order to do the compilation or the interpretation. Okay, so that's 3 different uses for trees. We represent these trees in different ways. For example, the world tree, each node can have a huge number of children. Right? So USA has 50 states, District of Columbia, Puerto Rico, and a few other little subjugated islands still. So 55 or so nodes. And each of those has a bazillion nodes. In the binary tree, we say, again, there's only 2 nodes. And so instead of having a selector called children, we have a selector called left child and a selector called right child. Okay? Sorry. Okay, so that's what a tree is. That's the general idea of trees. I haven't shown you any actual code yet. I'll get to that in a minute. What I want to do first is talk about the idea of a node. And a node is basically a piece of a tree. So this node represents the United States. The node is not just the datum USA. Sorry, it's the chalk dust. The USA node is this whole thing. It's the datum, the value, USA, plus all the children and grandchildren and grand-grandchildren and so on of this node, okay? So, what's the difference between a node and a tree? Come on, no hands at all. A tree is a bunch of nodes connected. Well, but this node is a bunch of nodes connected, too. Somebody, yeah. Okay, he's saying a node is part of a tree, and a tree doesn't have a parent. It's not part of anything else. Well, that could be, except what I didn't tell you, if only I could find my chalk, is that there's this tree called solar system. And it also has nodes, Venus and Mars, and so on. So has this just stopped being a tree? Okay, so it's a trick question. The answer is there is no difference. A tree is just a node that we happen to be thinking of as the thing that we're looking at right now, the important collection. I'm emphasizing this because data structures textbooks almost always get this wrong. They think that there's a difference between trees and nodes, and as a result of that, they build way too complicated abstract data types. And as a result of that, their programs are humongous, and people get the idea that trees are a very difficult thing to work with. But if you understand, as you guys do, that a tree and a node are synonyms, then you will be inoculated against the fear of trees that they're probably going to try to instill in you next semester. Okay? All right. So why are these things called trees? Well, it's because they look just like a tree in real life. In real life, a tree has roots in the ground, and then it has branches that grow out of the roots. And finally, it has leaves. Right? So a tree looks just like this. That's why it's called a tree. I once got to give this talk in Australia. It was so much fun because the trees do look like that down there. As I said, there's no built-in data type called tree in Scheme, and that's because you want different kinds of trees for different purposes. We're going to be looking for most of today and Wednesday at a particular kind of tree that has the property that a node can have any number of children, and there has to be at least one node. So in this world that we're dealing with, there's never any such thing as an empty tree. But other trees are different from that. When we talk about binary trees, for example, it's going to turn out easier to say that there are empty trees. In both cases, we choose what's going to make the programs easier to write. So you'll see after you've written some tree code why no empty tree for a multi-child thing and yes empty tree for binary are the right choices. Okay. Oh, up there is an abstraction diagram where the thing above the line that we're trying to create is this notion of a two-dimensional hierarchy. And the way we're going to implement it is with a constructor make tree. Sometimes you'll hear me say make node. They mean the same thing because trees and nodes. And selectors datum and children. And it turns out datum is just car and children is just cooter in the implementation that we're using. But as with any abstract data type, once we've created this abstraction, you're not supposed to think about it that way. So up here, we have the constructor and the two selectors for trees. And here's our first, above the abstraction barrier, tree program. It takes a tree node and says, is this a leaf? And a leaf node is one that doesn't have any children. Children is a list. It's a plain old linear sequential list whose elements are nodes. So a node doesn't have any children if its list of children is empty. That's what this procedure says. Any questions about that? So leaf question mark doesn't know anything about the implementation of trees, the sort of below the abstraction barrier representation of trees. It uses children, which is the abstract selector for the list of children of a tree, to find out. Now, that list of children, by the way, is not a tree. It's a list, a plain old sequential list linked together by cooters, and cars for the elements, like last week, in which the elements are nodes, are trees, in other words. So it's a list of trees. There's a name for a list of trees. It's called a forest, for obvious reasons. And there isn't any abstract data type for forest, because a forest is just a plain old sequential list. So like all plain old sequential lists, we can use car and cooter to find elements and sublists, respectively. Is there a question? I thought I heard somebody, but I don't see a hand. Okay. 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 So here's T1. One, two, three, four. Five, 6, 7, 8. So this is the list, the tree T1. If I actually print it out in Scheme, it looks like that. But you're not supposed to worry about what it looks like. What you're supposed to worry about is probably the most beautiful piece of code you're ever going to see in your life, which is tree map. And to show you what it does, I'm going to say tree map square T1. And it gives me another tree like this, where each datum is the square of the corresponding datum in T1. So it's a tree with the same shape as T1, and I've applied a function to every datum in the tree, not to every node, because a node is the datum plus the children, but to every datum, the things at the nodes in the picture. And I get back something that's the same shape as the input, no matter how complicated the input tree may be, applying a certain function to each datum in order to get the result. And we do that with 4 lines of Scheme. And I hope you realize how impressive this is, because of the fact that this is a complicated data structure. You have to kind of wend your way through it and look at all the children, and don't forget the datum of the node you're at, and so on. And this little program does all that. How does it do it? Well, what data type, first of all, should the result of calling tree map on a function in a tree be? What do you get back? A tree. How do we make trees? We use the constructor makeTree. Now, makeTree takes 2 arguments. The first one is a datum. So what datum should we put at this node we're constructing? And for that, we just apply fun, the argument function, to datum of tree. Okay, everybody clear how that makes sense? We're given a datum and children. We call square, in this example, on each datum. So now we have to say, what should the children be? Well, the result of the result of calling tree map on, let's say, this node right here is this node right here. Okay? And in general, in the result, we're going to have one child in the result for each child we have in the original, right? And what is it that we do to those children? Well, we tree map them, because each node is a tree, right? So what we want to say, basically, is map, tree map, children of tree. We can't quite say that, because tree map is a two-argument function. So I have to say instead, map, map, lambda of child, tree map fun child over children of tree. And that's it. Wow. Was that easy? Where's the base case? Say it louder. In the map. Yes, buried inside of map is, if this is an empty list, then just return the empty list. Do you have a question? That was your question, okay. So, what's going on here, if you think about it hard, is actually pretty complicated. When is children of tree, when is the argument to map going to be empty? Well, two cases. One is children of tree is empty. What kind of a node are we at? If children of tree is empty. Your choices are root, branch, and leaf. Leaf, we're at a leaf node. So that's a kind of vertical base case. We've gone as far down as we can go. When else is map going to be called with an empty list? Besides being at a leaf node. All right. Let's say we're doing tree map of this node here, the one that starts with 5. And direct your attention to the children of 5. Even for a leaf node, this is not just a 6. It's a node whose datum is 6 and whose children is the empty list. Okay? But what we have is a list of 3 nodes. So map is given this list of 3 nodes, and it cooters its way down the list until finally it runs out. Okay? So one base case is the sort of vertical end of things when we're at a leaf node, and the other is a kind of horizontal end of things when we've run out of siblings. Right? Neither of which is explicit in this code, because map just takes care of it. And we're leveraging the abstraction of a linear sequential list to help us build the abstraction of a two-dimensional hierarchical tree. Okay? You are not going to totally get this piece of code sitting here in the room today. You're going to go home and take it home and stare at it for hours and play with it and poke around inside it and trace the calls to map until you finally get it. But you will see that these 4 lines here are like the most beautiful thing in the universe. Just an amazing thing that we can do that. And it's not, by the way, that I got to write this beautiful thing because I'm brilliant. It falls out of the nature of abstract data types. Yeah. So the running time? Basically, you have to look at each node, at each datum, right? So it's linear in the size of the tree. Unlike the case with the binary search tree, where we could avoid looking at some of the data. And so it's only proportional to the depth of the tree rather than to the total number of items. But here, we have to look at every item. Okay, so a two-dimensional data structure gives rise to a kind of two-dimensional control structure as you're tracing out what's going on here. You're going to start with a node, and you're going to look it through its children and go left to right in the children, but within each child, you're going to go top to bottom. So what's the order in which the computer actually figures out squares of numbers? Well, it depends on the order in which STK chooses to evaluate arguments. The scheme standard does not say the leftmost argument has to be evaluated first. That's left up to the implementation. Some go right to left. I don't know of any that do something other than left to right or right to left, but it's imaginable that they might do the easy ones first or something. So we don't really know, but let's say it goes left to right. In that case, first we square 1, then we square 2, then we square 3, then we square 4, then we square 5, then we square 6, then we square 7, then we square 8. So that's the order in which things actually happen. So it's 1, 2, 3, hit a base case, back up to 2, down to 4, hit a base case, back up to 2, hit a base case for running out of children, back up to 1, down to 5, right? That's how it goes. And all of that incredibly complicated up and down, left and right structure is in this call to map that calls tree map, but it's not tree map calling tree map, it's map calling tree map, right? So I mentioned last time the idea of mutual recursion. And what we have here is a mutual recursion where tree map calls map and map calls tree map more than once. Map calls tree map as many times as this node has children. Okay, whichever node we're looking at. So that's what gives rise to the two-dimensional control structure, is the mutual recursion. Yeah. Can we do it without mutual recursion? Yes, but you're not going to like it, the answer. Anything, it turns out, can be done iteratively, just, with one tail call. But the cost of doing that is that you have to build explicitly yourself a data structure full of unfinished tasks. So in essence, you have to write a little scheme interpreter on your own that remembers what parts of this problem it hasn't solved yet and goes through them systematically. So you really are doing the equivalent of a mutual recursion, but you're doing it in a more complicated way. But it is, it's iterative. So that used to be, as I said, that used to be really, really important in the days when computer memory was expensive and small. People were happy to find iterative equivalents to recursive programs. Today, if you're dealing with a two-dimensional data structure, please don't try to do it iteratively. Okay? Mutual recursion is your friend. Enjoy it. It lets you write tiny little programs like TreeMap. Other questions? Yeah. Say it again. Yeah, if you're doing something in 2 dimensions, you should naturally think about mutual recursion, yes. And in particular, you should think about this trick of using map to handle one of the dimensions for you. Okay? The vertical moves are sort of handled by this call to children right here, which is outside of the map. But inside of map is where we deal with horizontal motion across siblings. Okay, great. Speaking of mutual recursion, Here's tree map done without using map to make the pattern of behavior even clearer. So instead what I did is I invented a helper function called forest map that looks a lot like map, but it's specific to tree map. So forest map function, and the second argument is a forest, which is to say a list of trees, a different thing from a tree. So when we're dealing with a tree, we say datum and children to get the pieces of it. When we're dealing with a forest, we don't say datum and children. It doesn't have a datum and children. It has elements that are trees, and so we call car and cooter. Car gets one tree, cooter gets a slightly smaller forest. Okay? So it says if the forest is empty, return the empty list. So here's the base case, both vertically and horizontally. Otherwise, cons, what should the car be? Well, it should be a tree. And we get one by calling tree map on car forest, which is the first element of the forest, which is a tree, because each element of a forest is a tree. And then what should the cooter in the Sculpta cons be? Well, it should be a forest, which we get by doing forest map of cooter of forest. Okay, so the pattern of the recursion tree map calls forest map, which calls itself recursively and also calls tree map. Okay? So that's the sort of dependency picture for these two procedures. And that circularity, tree map calls forest map calls tree map, that's what makes a mutual recursion. Yeah. What does a forest look like? Forests don't have branches because they're not trees. A forest is just a plain old linear list like we learned about last week. So it looks like this. Right? And each of these cars points to a tree. What does a tree look like? None of your business. It's an abstract data type. Okay, you're not supposed to think about it. You're supposed to think about this is a tree. This thing is a list of trees, and that's that. Okay? All right. Okay. Oh, I forgot to make an administrative announcement, so let me back up and do that. The administrative announcement is the instructions for Project 2 are in Volume 1 of the Reader under the Week 5 homework page. So the actual project, the problems that you're doing are in the textbook, but in the Week 5 homework page, it tells you how to load the file that you need and how to actually run it and see pictures on the screen. Also, when you turn in the project, you don't have to turn in pictures. In fact, you shouldn't print pictures on the lab printers, if possible. You should just turn in your code and a transcript of the kind of debugging that you can do just looking at values on your screen. Okay, so that's the administrative announcement. Somebody asked me before class, do we need blue books? No. No blue book, no Scantron. The only thing you should bring with you is your 1 page of notes. and a good book to read. Somebody asked in office hours about abstract data types, and I said, there are two sort of opposite mistakes you can make. So let's talk about trees and forests. One mistake, the most common one, is to just ignore data abstraction. So up here, where it says datum, I would see car. And down here, where it says children, I would see coulder. So that would be violating the tree abstraction. But the other kind of data abstraction mistake would be to say datum here. Because this thing, forest, is not a tree. So it doesn't make any sense to ask for its datum or its children. Yeah. The abstraction of datum and children, no, it's not. I defined those procedures right at the beginning of class. They're the first 3 lines of code were define make tree, define datum, define children. To be cons, car, and coulder, respectively. Okay. Yeah. Would it be yes? If we call car on the tree, like for example here, that's a data abstraction violation. You should imagine, once we've built make tree, datum, and children, you should imagine that you have no idea how trees are represented. They're a data type that came with scheme, and the only kind of insides they have are a datum and children, and they're completely unrelated to car and coulder. Yeah. Why do we call car for a forest? Because a forest isn't a tree. A forest is a list of trees. So I wouldn't say car of forest, because car of forest is a tree. Okay? But forest itself is not a tree, so it's okay to take its car and its coulder. Does that make sense? Okay. Yeah. Yes, that's right. You will not be asked to draw box and pointer diagrams for a tree. I want you not to think about it in those terms, actually. Okay? All right, moving right along. Another kind of two-dimensional data structure, lost my chalk again, behind me. Thank you. Another kind of two-dimensional data structure is a deep list. My favorite example this is not a tree like those ones I drew on the board, because it's not a sort of infinite depth kind of thing. It's a list of lists of words, or in other words, a list of sentences. Okay? And ordinarily, I would write a program to manipulate a list like this by using car and coulder for the elements of the outer list, and first and but first, probably, for the elements of the inner list, because I'd say those are sentences. All right? But right now, I want you to kind of squint a little, look at it sideways, and say, this is kind of like the following tree. Okay? See the connection between this picture and this picture? Now, this is a funny sort of tree. It isn't like the trees we've been dealing with because the branch nodes in this tree don't have data. So there's a very sharp distinction between a leaf node, which has a datum but no children, and the other nodes, which have children but no datum. Okay? So it's not an example of the abstract tree structure that I built a few minutes ago. But it is a tree-like thing. And we can use tree-like code to manipulate it. So if I wanted to do something to every word of this thing, and I wanted to figure out how to do that, one approach I might take would be to write something that looks a lot like tree map. Except that it wouldn't talk about make tree or datum or children because we're not using that abstract data type. Instead, it would say, this. And what this code says, it's not as pretty as tree map, but it's not too bad. It has an if. For tree map, for every node, we have to do something to the datum and also do something to the children. In this kind of deep list, a node has only a datum or has only children, depending on whether or not it's a list. If it's a list, it has only children. So I do this thing, which calls deep map by way of map, just like tree map called tree map by way of map. But instead, right here, where it used to say children of tree, here it just, LOL, by the way, does not stand for laugh out loud. It stands for list of lists. So you kind of want to be seeing children of LOL here, but a branch node is its children. A branch node is just a list of its children. So there's no selector needed for finding the children of a branch node. A branch node is a list of children. And at the other end of things, if it's not a list, then it's a leaf node, and the leaf node is just its datum. So instead of calling fun of datum of LOL, we just call fun of LOL. All right? So in tree map, every call involves both of these pieces. In deep map, there's an if, and we do only the thing for the datum or the thing for the children, not both. And that applies to the whole node. All right? So that's what you get by kind of squinting your eyes at a deep list of lists. And it could be a list of lists of lists, and this mechanism would still work. It could be an arbitrary depth list of lists of lists. Okay? So it's better than something that you would write just for lists of sentences. List of sentences one might be easier to read for this particular situation, but this one, this deep map, works on lists of sublists of sub-sublists of sub-sub-sublists to varying depths and varying places, however you want, just like trees can have varying depths. Okay? So, just to make your life unbearably complicated, Okay. The book, confusingly, uses the word tree to mean what I'm calling a deep list. I use the word tree as a broad generic term for any of these two-dimensional data structures, including the list of lists, the capital T tree, the binary tree, any other 2D structure that we come up with where each node has one parent node, or except for the root node. Okay? So me, this is a generic term. Them, they mean deep list. So they have a thing called tree map that's like my deep map. Okay? Just to confuse you. When you see tree with a capital T, it means this thing with datum and children as selectors and make tree as the constructor. Okay? So that should be true, for example, on an exam. Not this exam, which doesn't cover this stuff, but midterm 2, if you see capital T tree, I want you to know what that means. Okay? What are we doing on time? One last question. Yes? Does scheme deal with nodes that point to their own parents? Is that what you're asking? Yes. We are going to talk about circular structures, but not for another month or so, because they're pretty hard to deal with satisfactorily. But yes, we are going to. Okay, see you Wednesday. Twice.